Hello, my name is Arun Mukundan and today I will be presenting my thesis, Local Descriptors for Image Matching and Retrieval. So first, let us see what are local features. Basically, given an image, what we want to do is detect some salient regions which are characterized by their location and their shape. Given these regions, we want to normalize them to canonical patches. And given these canonical patches, we want to extract d-dimensional vectors called local descriptors. Now, where are these local descriptors useful? So let's have a look at what happens during image matching. In image matching, we are given a pair of images and we independently do the same procedure on both images, which is basically to find salient regions, normalize them to canonical patches, and extract a d-dimensional vector for each such patch. And what are the properties of this vector that make it attractive is that we want that the vectors that describe the same 3D structure should be similar in Euclidean distance, for example, and those that do not depict the same 3D structure should be far away. So given this condition, what we do in the matching stage is basically that we look at this descriptor corresponding to this and we compare it to every descriptor in this query image, and we find the nearest neighbor. If this nearest neighbor is below a certain threshold, then we call it a matching descriptor, and if not, then this is non-matching. So this is a simplistic view of image matching. And what are the other tasks that it can be used in? It can be used, for example, in structure from motion, where we are given a large database of images and we want to find a 3D point cloud corresponding to a 3D scene it depicts. In visual localization, the situation is opposite, where we have a point cloud and we want to localize the camera position and orientation based on the image it is seeing. And lastly, we also have image retrieval, where we have a large database of images, and given some query image, we want to find those images that are visually similar. Now, let's look at some of the work that has been done in local descriptors so far. It mainly falls into two schools of thoughts: handcrafted descriptors and deep local descriptors. We have some examples of each here. And the advantages of handcrafted descriptors are that they are intuitive, they are tweakable, but they do not perform so well on modern benchmarks. Whereas in the case of deep local descriptors, they require a lot of training data, which needs to be given at patch level. They have around 1 million parameters, so the behavior is difficult to interpret, but they perform very well on modern benchmarks. So let's start our journey into this. In our work, basically, we have one contribution to handcrafted descriptors and one contribution to deep local descriptors. So I would like to start with the handcrafted one. Let's start by looking at a familiar descriptor, SIFT. So I hope everyone here is familiar with SIFT, but a simplistic view of SIFT is basically like this. We are given a patch, we quantize it into spatial bins. Now in each of these bins, we find gradient orientations for all these pixels, and we quantize it again into orientation angles, and now we have a histogram for each bin, and when we concatenate all these histograms, we get the final descriptor. So once again, it is basically a concatenation of the histogram corresponding to each bin. As you can see here, what we are doing is we are actually encoding the position and the appearance of each pixel of each bin by doing this concatenation. But we can also look at it in another fashion. We can actually see it as an aggregation of pixel embeddings, which basically means that instead of considering this bin, what I imagine is that there is one pixel here, and I take its contribution towards the histogram, and I assume that the rest of the patch has no pixels at all. So basically what this gives me is a one-hot vector, and an aggregation of these vectors finally gives us the same histogram that we saw before. In this case, this can be expressed as a summation of pixel embeddings. Now, what exactly are these pixel embeddings and why are they useful? We can see why they are useful when we look at the inner product, which is basically when we try to compare two patches to see whether they are similar. As you can see, this part is the aggregate for patch P, and this part is the aggregate for patch Q, and this expands out to give us this particular expression, which basically says that we are comparing every pixel in patch P to every pixel in patch Q. Now, we are comparing every pixel in patch P to patch Q, but what exactly is the comparison look like? So, the comparison by the inner product that compares pixel embeddings basically just uses a joint kernel over the position and the appearance. This is going to be a consistent theme, so we will always divide things into position and appearance. And now, what do the kernels in each of these look like? Not exactly kernels, but these functions, similarity functions. So we can see that it's actually something like a step function, and it is definitely not smooth. I would like to remind you here that we are just ignoring multiple assignment for now to have the simplistic view. But in any case, one straightforward continuation is that instead of having this step function, we can have a smooth similarity. So basically what I want to say is that given these attributes, again either of position or appearance, we first map them out onto a domain, and for every point in this domain we construct a d-dimensional vector. And what is the advantage of constructing this d-dimensional vector? By the way, we call this d-dimensional vector the embedding. The advantage is that when we take the inner product of two instances of attributes p and q, then what we get is that the kernel is based only on the difference of these two, and in this particular fashion. So when the dimensionality is low, the approximation is not as good, but when the dimensionality is high, the approximation is quite good. Now, how can we use this to embed position and appearance? We use what we call our kernel descriptors. So we specifically design Cartesian and polar kernels such that the Cartesian kernels are tolerant to errors in translation that the detector might make, and the polar kernel is tolerant to errors in rotation that the detector might make. And as you can see here, based on the position encoding that we choose, we have to choose an appropriate appearance encoding. Now, as I said before, the Cartesian one, the advantage of the Cartesian one is that it is stable around the center and that it is tolerant to errors in location of the precise location of the key points. Whereas the polar one is tolerant to rotation mistakes, but there is a marked discontinuity around the center. So what we want to do is we want to have the best of both worlds, and in order to do this, we want to concatenate these descriptors. And on top of this concatenation, we introduce a simple learning procedure that will take care of co-occurrences and also take care of the mixing ratio in which we concatenate these. So we use a simple widening transform called a linear discriminant projection, which was introduced by Char, Nikolaitzik and Matas in PAMI 2010, which basically consists of a simple affine transform. The supervision is in form of similar pairs, and what this automatically does is it also finds an optimal mixing ratio and allows us to visualize the behavior of this learned transformation. And it's basically carried out in two steps. One is to whiten the space of differences, and the second is to rotate to preserve the discriminative directions of this whitened space. Now, once we use this, we can visualize the behavior of the learned transformation. So let's see what this behavior looks like. So here what we are showing is the similarity given the position of some query pixel to every other pixel in some target patch. Now, the first thing we notice is that the difference between these two angles is 0 in all these cases, but in spite of that the kernel is changing, which means that this is not shift invariant with respect to the gradient orientation. And secondly, we also find that it actually follows the angle of the gradient. So what does this actually mean? We propose that this means that it's potentially handling overcounting along edges. What I mean to say is that given an edge and a pixel in a patch P, let's say that there exists a similar matching edge in patch Q. Now, since we saw that these descriptors are actually match kernels, it's going to compare this pixel in patch P to every pixel here, potentially leading to some overcounting, and the shape of the kernel adapts to overcome that. So this was our first contribution. And before we head on to the second contribution, let's try to characterize handcrafted descriptors once more. So it basically proceeds in 3 steps, which is measurements, pooling, and post-processing. So first, in the step of measurements, we have in our case we took gradient orientations and magnitudes, and we embedded them using a kernel descriptor. Now, in the second step, we use some pooling, which can either be like aggregation over some spatial bins and then concatenation, or spatial encoding as we used. And the third is training or post-processing, which in our case was an affine transformation. Let's try to contrast this with deep local descriptors. If we do that, we can see that the steps are pretty much the same. We have measurements, pooling, and then end-to-end training. In the case of measurements, we have a fully convolutional network, and you can see that these measurements are slightly more complicated and not so easy to interpret. In the pooling step, basically we can interpret it as a concatenation of the activations from the top layer, and then a fully connected layer which consists of some weight W. And finally, in the end-to-end training part, we learn the parameters of these networks. Let's have a closer look at this pooling stage. What we say is that this FC layer is actually doing implicit spatial encoding. And why do we say that? So let's have a look at what's happening here. We have this tensor which describes appearances, and we have this final descriptor here and a weight matrix here. And what does the similarity look like when we compare two descriptors? So the similarity looks like this, where again it is divided into an appearance part, and there is this weight here. Now let's have a look at a closer look at this at the structure of this W transpose W. In order to do that, we cast this thing slightly differently, and instead of expressing it as a concatenation, we express it as a sum once more, as we did in the case of SIFT. So in this case, we find that actually this huge weight matrix that we have decomposes into one transformation matrix for each vector of vector at each position. So for example, let's say that this is the position 1, 1, then this is the vector of activations, and this is the corresponding transformation matrix. And similarly for 1, 2, 1, 3, etc., etc. Now, what is the advantage of looking at it in this way? If you look at it in this way, again, as we did with SIFT, we have this aggregate, the inner product is an aggregate, transpose an aggregate, which opens out, and we are basically comparing every position in patch P to every position in patch Q. So actually the structure of this matrix W transpose W consists of a set of blocks, where each block is defining the dependence of the position in patch P to the position in patch Q in this fashion. So that's why we say that W transpose W is actually performing implicit spatial encoding. But given that this is just spatial encoding, can we extend the lessons that we have learned previously to this case as well? We see that we actually can, and we define explicit spatial encoding in the following fashion. It's not something that we came up with, it is previously in literature as well. So we encode the position using a pre-computed spatial kernel, whereas before this is the tensor of appearances, and now instead of a transformation matrix corresponding to every single position, we have a spatial embedding corresponding to every single position, and we take a Kronecker product. And when we do this, the similarity basically decomposes into this spatial part and this appearance part. So this appearance part is basically the inner product of these vectors, whereas the spatial part is something that we define. For example, we can have it as a Cartesian or a polar thing, same as before. And finally, as before, we apply an affine transform to reduce the dimensionality. And similarly to deep local descriptors, the parameters of the affine transform and the fully convolutional part are learned in end-to-end fashion. And now what is the advantage of doing it in this fashion? The advantage is that we can greatly reduce on the size of the model, since we know exactly what it's doing and we are explicitly addressing it. So the conventional deep local descriptor that we look at is a hardnet, and as you can see, it has about 1 million parameters. Whereas something that has less than half the number of parameters still has the same performance. So here S is equal to 1 controls the dimensionality of the approximation, as we had said before. Another thing I would like you to notice here is that the number of parameters for our model stays constant irrespective of the path size. Whereas in a conventional model, if you increase the path size, then the number of parameters explodes. And all this while keeping the performance constant. Another thing we can see is that when we use sum, we are discarding spatial information, so the performance is much lower than when we use concatenation. And finally, let's look at a comparison with state-of-the-art. In this case, we see that this is a graph of performance on the H patches benchmark on 3 tasks, which are matching, retrieval, and verification of patches. And this is arranged chronologically. And we can see that earlier it was usually dominated by handcrafted approaches, and as we move into the future, there is being dominated by deep local approaches. When our handcrafted descriptor was introduced, it was performing quite well even as compared to the deep approaches. And finally, this is our descriptor that we have recently introduced, which is the deep local variant. Now, let's finally come to the last part of our thesis, which is robust data whitening. First, let me explain what is data whitening. So, in data whitening, we are basically given a set of data points x, which you can see here, which has some covariance sigma, and we have some defined transformation based on the parameters p and mu z, such that the covariance of the points z in this whitened space is identity. In other words, it diagonalizes the covariance matrix. So this is an affine transform. It's given by, the solution of this is given by P transpose P equal to sigma inverse, and it is not unique. Basically, what I mean to say is that given any rotation, the solution still holds. Now, what we are looking at is robust data whitening. So let's reformulate this slightly differently. Let's look at all possible transforms P of x minus mu, and let us constrain the determinant of P to be equal to 1. Then in this case, let's say we want to minimize some particular cost. So actually, if that cost is an L2 cost, then a closed form solution exists and can be described as follows, blah 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 blah. But the problem is that when we use L2 distances, it's sensitive to outliers. So instead, we want to minimize some other cost which is more robust. And if we want to do so, we can use the procedure of iterated reweighted least squares, given that certain conditions are satisfied. And basically, we can show that if this cost is the L1 cost, then these conditions are satisfied, and indeed we can find a global minimum to this cost. Okay. Now let's have a look at, let's visualize and see what's really happening in this case. So we present some synthetic examples. In the first case, we have this set of data points which is drawn from a Gaussian distribution with a certain covariance and mean, known covariance and mean, which we call ground truth. And in the second case, we have the same distribution, but we have added an outlier here. And now we see that when we use this procedure to estimate it, as we said, the ground truth was the covariance and distribution with which the distribution was generated. The conventional estimate is what we have when we use the L2 distances, and the robust estimate is what we get when we use L1 distances. In the case where there is no outlier, these are fairly close by. But as you can see, in the presence of an outlier, the robust estimate still stays fairly close to the ground truth, whereas the conventional estimate deviates significantly. We can also try to find out how this works empirically by checking its performance, by testing it on some image descriptors. In this case, I would like to mention that these descriptors are not L2 normalized. Actually, we found something interesting, which was basically that when you use this robust whitening and you use an L2 norm, okay, Andre Yorgos, I need to think about this part slightly more, so I will skip this for now. And finally, we come to the conclusions of the thesis. So these are the 5 conclusions. The first one is that quantization effects from spatial encoding can be alleviated by using kernel embeddings. The second is that using multiple kernels captures richer information, producing more discriminative features. The third is that the fully connected layers of deep local descriptors implicitly encode spatial information, and when we explicitly encode the same information, we can have the same performance with smaller models. And finally, we show that a robust whitening transform can be found by using an iterative procedure that is guaranteed to converge to a global minimum. Thank you.